Okay, so this is the 6th video for chapter 23 on geometric optics. This is actually the second part of the lenses video. I felt that 2 different videos would be appropriate here in the event that you feel you have the lenses down and you don't need to look at the examples that follow here. Then feel free to skip this video. Otherwise, enjoy yourself here. A converging lens of focal length 25 centimeters is used to produce an image of 5 centimeter light bulb located at a distance of 75 centimeters. What is the image location, size, orientation, and type? So quite a few things here. I'm just going to do a quick little sketch just to make sure I have those things down. So this is a converging lens. Looks like so. I'm going to go ahead and draw the principal axis. We have a focal length of about 25 centimeters. So I'm just going to go ahead and put that on either side here. So that's F. And I have some object that's located out here 75 centimeters away, and so that'd be distance to the object 75 centimeters. And if I were to just do a really quick little drawing here, I'd see that the image is going to be, let's see, somewhere, I think, if I remember, this looks like it's case 2 here. It's going to be over here somewhere, and then let's see, the one that goes through this. Yeah, it looks like it's going to be between, if I remember, it's between F and 2F on the other side, and that seems about right. So let's make sure that my image distance turns out to be between 25 and 50, okay, because I believe it's going to be between those two based on my ray diagram. Let's go ahead and use the lens equation. I'm looking for the image location, so I'm looking for DI. I'm going to go ahead and solve that equation for DI right away, or at least 1 over DI. 1 over F minus 1 over DO, and let's go ahead and plug in those numbers here. 1 over focal length is 25 centimeters, and that's a positive value here. Subtracting away 1 over DI, well, that's 1 over 75 centimeters, and that answer there is about 0.0267 inverse centimeters, so DI would be the reciprocal of that, and that would be about 37.5 centimeters. So sure enough, that matches what I thought we would have, something between 25 and 50, so I'm pretty sure I did that correctly. What is the image location? There we go. What's the size? Well, size is going to be from magnification, so negative DI over DO, so I'm looking for the magnification of this thing here. Let's see if we can go ahead and solve that. Negative, let's see, DI we said was 37.5 centimeters and DO was 75 centimeters, and so we get for that about negative 0.5, and again, the negative means that it's inverted. 0.5 means it's half as big, so if I'm looking for the size would be about 2.5 centimeters, and it would be its orientation would be inverted. Okay, and last thing, type. It is a real image. The light rays actually do converge there. Okay, so that's the first example. Let's take a look at the second one here. A diverging lens, focal length 0.42 meters, produces a virtual image distance of 18 centimeters in front of the lens. How far away is the object, and what is the magnification of that lens? So diverging, it's a little bit harder to draw here. Let's go ahead and do that here. Diverging lens, principal axis. The focal length we said is 42 centimeters. I'm going to put that in as a negative 42. Always pay attention to the fact when I say diverging, got to have a negative F there. I'm going to go ahead and keep that as centimeters since my image distance is 18 centimeters. Make sure those units are the same. Now it's in front of the lens, so if I consider the light rays traveling this way, this would be the front side. So the image is actually 18 centimeters on this side of that lens, and so DI would be 18, but I have to put in a negative here. Remember, this is an object, or rather an image, on the same side as the light that's entering that lens, so DI would have to go in as a negative. So I have 2 negatives here, focal point or focal length and distance to the image, both negative. Now this is asking is how far away is the object? Well, the object would be over here somewhere. It's going to be larger than the image. Remember, the virtual image created from diverging lenses would be smaller, but upright. And so I'm looking for DO. And certainly to find that, I'm just going to use the lens equation, 1 over DO. is equal to 1 over f minus 1 over di. Let's go ahead and plug in those numbers here. That's a negative 42 centimeters minus a 1 over a negative 18 centimeters. You can see that this is going to end up turning that into a positive. And when I'm all done here, I get 1 over do is equal to about 0.0317 inverse centimeters. So do, the reciprocal of that, is about 31.5 centimeters. And as expected, it's a positive value because it is on this side of that lens. That's what we should expect. So 31.5 centimeters for the object distance. What's the magnification? Well, magnification again is a negative di over do. So we have that negative there. Di is a negative 18 and do is a positive 31.5 centimeters. And so we should expect a positive value, which is what we have there. And divide that by 31.5, we see that the magnification is a positive 0.57. Okay, so that's example number 2. Okay, so it looks like another number 2 here. Sherlock Holmes examines a clue by holding his magnifying glass at arm's length, 10 centimeters away from an object. The magnifying glass has a focal length of 15 centimeters. Find the image distance and the magnification. Okay, then describe the image that he observes. So no, I'm not trying to describe the actual clue that he's looking at. I'm just talking about the image properties. So is it upright, is it inverted, enlarged, reduced, so forth. So let's do a quick little drawing here. Sherlock Holmes holding a magnifying glass. I know a magnifying glass is a converging lens, sort of like case 6 from my lenses here. So converging lens, focal length of 15 centimeters. And the object is 10 centimeters away from that lens. So if this is the focal point on either side, I have the object that's inside here. So this is where the object is being looked at. If we were to draw the light rays again here, it might help if we sort of determine again what's happening here to remember where the image is created. And these are diverging on this side. They all appear to be coming from a point back here. Okay, and I know I didn't draw that very well, but this is the virtual image. Our eye would have to be over here. So Sherlock Holmes with his hat must be on this side looking at that object here. So this is the enlarged image. So let's see, find the image distance. So I'm looking for how far this is, when I know that the object distance is 10 centimeters away. So DO is equal to 10 centimeters. Now, be careful here. This object distance is still a positive value. It's on the side of the lens that light is normally traveling, if you will. We're just going to view it from the other side. And so we're looking for DI. Let's go ahead and solve that for DI. So 1 over DI is equal to 1 over F minus 1 over DO. 1 over 15 centimeters minus 1 over a positive 10 centimeters. Let's see what we get for that. Yeah, I get that 1 over di is equal to a negative 0.0333 inverse centimeters. So when I reciprocate that, I get di is equal to a negative 30 centimeters. And that should make sense, that the image distance is actually negative. Okay, so that's because it's on the same side as the object is. Okay, so that's the image distance. So 30 centimeters on this side of that lens is where he sees that image. Find the magnification. So M again is a ratio of negative di to do, and so negative, we have a negative 30 centimeters and 10 centimeters. That would be a magnification of a positive 3. So he gets 3 times the view of that clue. Describe the image that he observes. Well, it would be virtual. It would be upright. And in this case, enlarged. Okay, so a good example there of a magnifying glass. And finally, our last example to complete this video. An object is placed 20 centimeters in front of a diverging lens, focal length 10 centimeters. Find the image distance and the magnification. Describe the image. Okay, so again, a diverging lens. I'm going to go ahead and show you the way that we typically draw this. Instead of drawing the actual lens out, we often just use a symbol that looks something like that. And so it's got a couple of focal points on either side. We do know that its focal length, when we see it's 10 centimeters, it really has to go in as a negative 10, okay, for that, because of it being a diverging lens. An object is placed 20 centimeters in front of that, so if this is f on either side, then we're going to have an object out here, and so a distance to the object would be a positive 20 centimeters. Find the image distance and the magnification. So if you recall here, the image is always going to be on the same side as the object here. It's going to be reduced in size. It's going to be located somewhere in here. And again, these are always a little bit tougher to draw. Right, so I'm just going to go ahead and try that here. This is sort of diverging, appears to be coming from here. Let's see, probably the easiest one to draw is this central ray. It continues on. This one's always tricky to draw, the one that looks to be going through F on this side and then goes out parallel. We're just going to draw these two here. This would be where the image would be located. From a drawing standpoint, we could do that all to scale, but much easier just to use the lens equation. So I'm looking for the image distance, so 1 over F minus 1 over DO. Just pay attention to those signs here. 1 over a negative 10 centimeters minus 1 over the distance to the object is 20 centimeters. And so what do we get for 1 over DI? We get a negative 0.15 inverse centimeters. So when I take the reciprocal of that, I get about negative 6.67 centimeters. Okay, so it looks like it's going to be in here, this distance, 6.67 centimeters on this side. That seems to be appropriate based on the fact that I know it's going to be closer to the lens. It's going to be upright, as we see there. Seems to be a little bit smaller. All of those numbers sort of seem to make sense there. So let's see, find the image distance I did and find the magnification. Well, magnification, negative DI over DO. Negative, here I have a negative 6.67 centimeters, dividing that by a positive 20 centimeters, and we get for that about a positive 0.33. So it looks like it's sort of reducing it by a factor of 3, turns it into 1/3 the size, but it does bring it a little bit closer to that lens. So in the event that I were trying to view that thing, I would actually see it a little bit closer than that distant object is. Okay, describe the image. So the image is virtual. It's upright. And it's reduced in size. So there we go. 3 or 4 examples for you on how to apply the lens and magnification equations.